Since existing gravitational observatories can only detect the strongest waves created in collisions of massive black holes and neutron stars, future detectors are being made with ever-increasing sensitivities to find more subtle changes in the fabric of spacetime. One concept being developed is called a pulsar timing array, which would allow scientists to probe Einstein's general theory of relativity and the effects of gravitational waves over thousands of light years. Since a pulsar is a rotating neutron star which emits a jet of radiation, if the beam of the jet points towards Earth, we detect a short radio burst. Those radio bursts arrive at regular intervals, sweeping across the Earth for every rotation of the pulsar. The fastest spinning pulsar, PSR J1748-2446 AD, which lives within the globular cluster of Terzan 5, 18,000 light years from Earth, rotates 716 times per second, which would sound like an F5 tone if the radio pulses were converted to sound. A spinning pulsar is of great interest because some pulsars' rotation rates are incredibly stable, so much so that they can rival the precision of atomic clocks. So PSR J1748, the fastest spinning pulsar, has been measured to rotate exactly once every 0.01395952482 seconds, with an error of less than 600 femtoseconds. This incredibly precise timing is one of the most accurately measured observables in all of astrophysics. By the way, this pulsar was discovered by Dr. Jason Hessels, who graduated with a Bachelor of Science in Honors Physics from the University of Alberta. The precision of a pulsar's rotation rate is very much like a clock, ticking at regular intervals. And just like the effects of gravitational Doppler shift, that redshift photons as they escape from a gravity well, gravitational waves alter the timing of pulses from pulsars. In order to actually do anything useful, though, you need several pulsars in an array. And now you know why they're called pulsar timing arrays. It may be easier to imagine pulsar timing arrays as similar to the technology that underpins the Global Positioning System, or GPS. The GPS sensors in smartphones and navigation devices work by listening carefully for radio signals from GPS satellites high in orbit above Earth. By comparing the arrival time of the pulses from each GPS satellite, your device can triangulate your position on the surface of the Earth. NASA's NICER Sextant X-ray telescope, which is on the International Space Station, is observing a collection of X-ray pulsars to test out the feasibility of using pulsar arrays as future navigational aids. By listening to the regular pulses from several nearby pulsars, you could triangulate your position anywhere in interstellar space around those pulsars. This map, created by the Jet Propulsion Laboratory, was affixed to the Pioneer 10 spacecraft, which, after completing a survey of Jupiter, became the first satellite with sufficient escape velocity to leave the solar system. The image shows the relative positions of pulsars near Earth, with their particular timings encoded on the line that joins them. If this map were discovered, the position of Earth could be deduced. But our civilization hasn't reached the point of navigating with pulsar timing arrays. Instead, we're patiently listening to them for evidence of large-scale gravitational waves passing in between Earth and the pulsars. When a gravitational wave passes in between the Earth and a pulsar, it causes a distortion of space-time that affects how signals propagate. Generally speaking, the signals from pulsars will either appear delayed or accelerated due to the influence of a passing gravitational wave. Just like a black hole creates a gravitational potential well and the associated effects of gravitational redshift and time dilation, so too can a gravitational wave create a measurable effect as it passes by. Imagine, for example, that you usually drive to work or school on a flat road. The time it takes you to get from point A to point B along your route takes about the same amount of time. What would happen if all of a sudden along the route a hill appeared? Or what if a depression appeared in the road instead? In both cases, the time it takes you to go from A to B will change ever so slightly depending on the size of the hill. A gravitational wave in space-time is just like this hill, only since it's a wave, it will be a moving hill. If the timing of a gravitational wave is just right, it compresses the space-time that the pulsar signals are traveling through, offsetting the arrival time by a small difference, which is called the timing residual. The timing residual is a measurement of the difference between the expected arrival time of the signal and the observed arrival time. Since gravitational waves can both stretch and squeeze space-time, whether the signal is delayed or accelerated will depend on the geometry of the pulsar timing array and the incident gravitational waves. So far, this method of monitoring pulsar timing arrays has not resulted in any observations of gravitational waves. However, techniques like these are a complement to the interferometer-based gravitational observatories and will eventually contribute to the detection of more massive binary collisions.